And I realize I'm talking on mute while giving my intro spiel. Uh, so, starting over, welcome everybody to the final meeting of 2025 for the Tucson Amateur Astronomy's Fundamentals Group. Today, we will be giving two talks. One, you see before you, on the constellation Gemini, just some facts and lore and objects behind the constellation for your upcoming winter observing sessions. And then after that, we will have Stephen Ferris be giving a talk on comets. And just to make sure, am I coming in loud and clear? Cool. I see some head nods. Awesome. And so without delay, let's go ahead and get right on into it. So Gemini is the 30th largest constellation out of the 88 modern constellations. It occupies about 500 square degrees in the night sky. Like all of the zodiacal constellations and many of the northern constellations, it is one of the original 48 constellations that were cataloged by Ptolemy in ancient Greece. But all of the zodiacs have their origin much further. They all date back to Babylonian myth, and we'll talk more about that here in a moment. The constellation itself is best visible in the night sky in the early evening from January to April, setting in early evenings by about May. The constellation itself houses 10 notable open clusters, 10 nebulae that are worth of interest, and 8 galaxies that are brighter than 13th magnitude. Outside of that, most of the galaxies will need some pretty powerful optics or pretty fast optics in order to make use of them. So we won't actually be talking about any of the galaxies tonight just because they're all really small or really faint. Additionally, it houses only one Messier object, in this case, open cluster Messier 35. And this is another one of the many examples that we have of the alpha star in the Bayer designation list not being the brightest star in the constellation. We'll talk more about that when we get to talking about some of the notable stars. Some other interesting things that come out that Gemini gets associated with is the December's Geminid meteor shower, which peaks the 13th and the 14th. And it typically has meteor fall rates of about 100 per hour, but nobody really likes to go see it, like the summer Perseids, just because it's cold in most of the parts of the northern hemisphere this time of year for that meteor shower, although I believe it's more observed this time of year in the southern hemisphere where they're approaching the height of summer. Another an interesting tidbit I did find while also researching in this is that both Uranus and Pluto were within the constellation Gemini when they were originally discovered by William Herschel and Clyde Tombaugh. And now know that they are no longer in this, but Gemini is now, not Gemini, Pluto is now somewhere well within the bounds of Sagittarius right now. So it's certainly traveled quite a bit since then. And it was also possibly home to the first instance of Jupiter, recorded instance of Jupiter occulting a star. Well, by which I mean that Jupiter was in the constellation Gemini when this observation was recorded. One of the first known occultations of a planet occulting another star, which was recorded in 337 by Aristotle. Moving on to some constellation lore, beginning with the Babylonians, which were the original progenitors of the constellation. They had known this series of sky to them as the Great Twins, much like the later Greeks would come to know them as being twins Castor and Pollux. Although for them, the two twins were representatives of their deity of plague and pestilence, as well as their king of the underworld, so their Greek equivalent of Hades. And they were minor servants of the Nergal, who was their king of the underworld. The twins were responsible for guarding the constellation Cancer, which we mark in the zodiac time frame marks the start of summer when the sun is within the bounds of the constellation Cancer. And this was significant for the Babylonians because being in a desert environment and what's now Mesopotamia, that they were very much not fans of summer. They regarded it as a time of death since they had just finished there no the rains had disappeared. There was no lowering water levels on the main rivers. There wasn't any time for harvest because of the extreme heat, and so they just regarded the start of summer with disdain. They did not like this, and so they were uh, assigned the and so Cancer for them held this sort of negative connotation within their culture. And so the twins were responsible for safeguarding and protecting the start of summer. In other instances of Babylonian mythology, the twins were also associated with Gilgamesh and Enkidu uh, during Gilgamesh's epic, where one of his tasks was the quest for immortality. And Gilgamesh's epic is essentially somewhat of a precursor to was one of the first major epics of history, but also served as like a prequel to Hercules' trials in Greek lore. Interesting book I did manage to find while researching this, which has a whole bunch of other Babylonian lore, is the book Babylonian Star Lore by Gavin White, which you can find on Amazon. And some of this, if you are interested in little tidbits of history and mythology along that, did seem like an interesting book to go check out. So a little bit of advertising there. Outside of that, most of what the constellation mythology that we know about Gemini comes to us from the Greeks and, in some sense, the Romans, because they copied and pasted a lot from the Greeks. And in their mythology, the constellation was associated with the two Argonauts, Castor and Pollux. Pollux himself was a demigod who was sired by Zeus, and Castor is the mortal son of Tyndareus, who was then the king of Sparta. So both Castor and Pollux, being twins, were played around with some Zeus shenanigans here, as he does like to do from time to time. And they were both princes of Sparta, which was significant for their culture because the Spartans were known for having dual kings, a dual kingship society, and so having twins was seen as a very great badge of honor to Tyndareus. Although the illicit origins of Pollux notwithstanding, the two brothers were also had two sisters who were specifically Helen of Troy and Clemenstria. Unfortunately, both brothers essentially died before the siege of Troy, so they were not present for the great battles there that were recorded in Homer's epics. But they were active during this time period, myth-wise. Uh, Specifically, though, the twins were used as patrons of travelers, sailors, athletes, and boxers, all of those attributed to many of their feats and activities that were found that they engaged in during the quest for the Golden Fleece with Jason as members of his crew. The boxing specifically comes through the activities of Pollux, who during that storyline won an important boxing competition during the quest for the fleece. Beyond that, how these constellations got associated with the night sky is a little bit funny. So, sometime after they had completed the quest for the Golden Fleece with Jason, they had gone back to their homes around Sparta and had joined two of their cousins in stealing some cattle from some ne'er-do-wells in Arcadia. So the four, succeeded in their raid, and on the way back, the two Idas and Licinius, who were their cousins, were like, "Hey, we'll have this eating competition, and we'll."
Connor, we lost your audio.
Hello.
Now I can hear you.
Okay, sorry. Cool. That was weird. My headset just randomly powered off during the middle of that. So, where was I? Nope. So, the two brothers decided that the two cousins of Castor and Pollux decided to have an eating competition to decide who gets the cattle instead of splitting it four ways. So they said that the top two eaters would get all the cattle, and the others would get nothing. And unbeknownst to Castor and Pollux, is Idas and Licinius were magical eaters, according to the myth, as in Idas was able to eat half an entire cow in one bite, and so they, much to their annoyance, lost this battle, and they did not get any of the cattle, while Idas and Licinius did. This really made the brothers angry, and they kept this grudge for a good while, as they were, sometime later invited to their cousins' weddings, still bitter about this loss. Uh, but Idas and Licinius were like, this is a wedding. This should be a happy day. Let's call a truce. And the twins, pretended to accept this, but remained mostly bitter still. And in keeping with Greek traditions, they decided as they were moseying around the party, they somehow stumbled into the brides of their cousins and had a love at first sight sort of tryst, and then promptly ran off with the brides and stole all the cattle that they lost. So during that last eating competition. So Idas and Licinius were, royally mad and proceeded to chase after Castor and Pollux, and before eventually killing Castor. And while Pollux ended up killing Licinius. And as Lytus was getting ready to strike and kill Pollux, Zeus intervenes and just throws a lightning bolt and smites Idas and says, "You're welcome, son." Pollux is distraught over the death of his brother and uses his newfound association with Zeus to like, "Hey, Zeus, save my brother. I'll give you half of my immortality." Knowing now that he's, a demigod of a demigod son of Zeus. And Zeus agrees, but he says, "If I do this, you're going to have to spend half your life in the heavens and half your life below the earth in Hades," which corresponds to the 6 month cycle where Gemini is visible in the night sky, being for 6 months of the year and below the horizon for 6 months of the year. And they agree, and Zeus tosses them all up in the night sky. So that's it for interesting lore. I mean, the Greeks are fond of their crazy stories. Moving on to some objects of interest that you might like to go look at. Starting with a giant list, we'll only talk about three of the stars. Two of them are on this list. The third is not. And one of the open clusters and two nebulae, which are not visible in this list because this list does not include nebulae, unfortunately. We won't be talking about any of the galaxies. Just they're all very small. Would require significantly powerful optics to make anything out of them. Which in my personal preference of keeping it with like things that you can do with reasonable levels of gear for an amateur, I'm not going to talk about any of that. So first off, is Pollux, otherwise known as Alpha Gemini. This is the second. I had this backwards. This should be Beta Gemini. I apologize. I had my names. But this is a K class orange giant. It has a magnitude of about 1.4 stoles, so about just slightly brighter than the sun. But it has 2 times the sun's mass, and it's almost 9 times the size of the sun. So it's keeping with a giant class, is very, very big. And it sits around a measly 34 light years away. The star is actively like Vega in the summertime. Pellix is used for calibrating scientific instruments, specifically spectrographs, since 2006. And prior to 117 BC, Pollux was interestingly enough in a position to be occulted by the moon. And given axial tilt of the Earth, this is actually out of place. But it would have been pretty cool back then to just look up and just see the moon move behind move in front of one of the brightest stars in the night sky. Pollux does have a potential exoplanet. There's a little bit of dispute around whether or not it's still there based off of readings. I think it was only confirmed by radial velocity measurements, and there's still some argument back and forth if it's not something else. But regardless of its disputed status, the International Astronomical Union did designate the planet as Thestius, which is a reference to Castor and Pollux' mother. They didn't name the star after the mother directly because Jupiter has a moon named after their mother, and so they didn't want to reuse the name for two different purposes. So they went with Thestius instead. Showing the position here in the night sky. So Pollux represents the left twin. If we were looking at the constellation Gemini from their standing quote unquote positions. And on the left, we also see a Hirschsprung-Russell diagram showing where the star lies. So being a giant, we would expect it to be well off of the main sequence diagram, the main sequence channel, which is over on the left, which we do. After that, we have Castor, which is an intriguing star system all on its own. It is actually a set of three groups of binary stars. So it's a 6-star system with 3 pairs of individual binaries that are all co-orbiting each other. This 6-star system has a combined visual magnitude of about 1.58. I won't go into the individual details about the 6 stars. It would take far too long. But regardless, we see on the right-hand side here, this is a chart showing the orbital separation of each of the individual components in the system, showing that the A pair and the B pair have an are separated by about 3.9 arc seconds, and this A-B pairing is then co-orbiting around the larger C pair, and with a separation of 71 arc seconds. So there is quite a bit here. Unfortunately, most of the stars are dwarfs, and so very difficult to make out the individual components. I believe I'm trying my slides. The star Castor AA and Castor BA are both A-class main sequence stars, which provide much of the illumination from this sextuple star system. With the C pairing having the dimmest of all, I believe both of those are both red dwarfs, so they have a very low brightness of about 9.8. So very interesting stellar dynamics. I don't think we've seen this. I've talked about a sextuple star system when we've talked about other constellations. So having it being one of the brightest stars in the night sky is definitely really cool. Although seeing all of them might itself be an interesting challenge. Castor itself is taking up the right-hand side of the twin and falls like most of the stars here. They do fall somewhere on the main sequence diagram. So the Hirschsprung-Russell diagram here on the left, I believe, is pointing out the brightness of the AA star, which is the brightest on the constellation overall, and not the individual components. Also looking forward to this time of the week. This time of year, Jupiter is currently in Gemini, as well as the moon when I was taking these screenshots earlier in the week. So definitely some interesting things to go look at. A constellation that is otherwise kind of boring. The way that I help keep myself, because it is kind of confusing on which one is Castor and Pollux sometimes if you're not fully familiar with the orientation of the constellation. But if you're familiar with where Procyon is, you can remember that Pollux is on the side closest to Procyon in Canis Major, and Castor is on the side closest to the bright star Capella in the constellation Auriga. So you can associate C is closer to C and P is closer to P when you're trying to keep these two stars right in your head. If you are doing anything like the Astronomical League's constellation diagramming challenges. The last star we'll talk about is known as U Geminorum, or just abbreviated here, U Gem. This star is what's known as a cataclysmic variable, which was discovered in 1855, although they didn't recognize it as a cataclysmic variable. They just recognized it as a variable star at the time. And it was found by astronomer J.R. Hind. And later,
We lost your audio again.
You guys hear me again? There we go.
Now we can hear you.
All
Yes.
right. I'll need to get a different headset for this if this happens again. I apologize for the interruptions. So the star itself is a white dwarf that is siphoning material from a smaller red dwarf. Normally, we would attribute this phenomenon to the creation of nova, which is the typical mechanism of a white dwarf accreting matter from a from a nearby companion star. But this is similar in that vein, but the mechanism that triggers the nova is different. So U Geminorum, in a classical nova, when the white dwarf is accreting matter from the sibling star, as the material collects on the surface of the white dwarf, it triggers thermonuclear explosions. Excuse me. However, in U Geminorum, rather than the mechanism for the novae occurring on the surface of the star, we believe it arises from instabilities in the disk of material before it falls into the star. So it has significantly less bright eruptions than you would expect out of a full classical nova, which makes it a little bit harder, has lower luminosities as a turn. The star has, being a binary pairing in order to become a cataclysmic variable, the orbital period of the two components is about 4 hours and 11 minutes, which would, corresponding to the very small size of both stars, one being a white dwarf, the other being a red dwarf. They had to be very close. So you won't go, don't go expecting to separate out the two individual components with this particular star. I do not have a position of it in the night sky on a star chart for you, but the RA and deck is here for those that are wanting to hunt it down for maybe some variable star programs. The two components are separated by the distance of 1.5 solar radii. So this is, off the top of my head, about 750,000 kilometers. I think the sun is about 1 million miles in diameter, kilometers in diameter, somewhere around there. So very small distance, slightly, I think about 4 times the distance between Earth and the Moon is how far these two stars are separated. Back of the napkin math checks out. But this is also an irregular nova. So it, on average, erupts about every 105 days. So depending on where we are in the current cycle, we may get lucky. Although it does have a very wide distribution. Some eruptions can occur in as little as 62 days, others in, over a year, slightly under a year. The white dwarf component is roughly the size of the sun at 1.2 solar masses, but being a white dwarf is very, very small at 8.008 sols in size. So, roughly the size of Manhattan by typical white dwarf standards. The red dwarf clocks in at just slightly under 1/2 of the solar mass and has a diameter of about 1/2 that of the sun's. So very small star overall. The star itself also has the combined visual magnitude of the two components ranges between a 14th magnitude and 15th magnitude. So you would probably need something around an 8-inch scope to see these stars during their normal activity. Although if you get lucky and we are seeing it during a nova outburst, this can push the individual component up to 9th magnitude. And making sure my headset doesn't decide to turn off on me again. On to the 3 notable deep sky objects that we'll talk about tonight. First one, jumping ahead of myself. So this is a rough photographic rendering of the totality of what's inside the constellation Gemini. You can see that it's mostly stars and open clusters. There's not a lot of extended nebulosity in it. We have, extended nebula over here near the foot of Castor, over by the constellation, over by the stars Propus and I don't know what the Greek letter for lowercase u is. So the star I was mentioning with U Geminorum is not the same U Geminorum here. This is I forget what the Greek letter for U is. That's used in the micro units, but not the same star. So it's not this one here. The U Geminorum I was talking about is actually like somewhere over in this area, far off to the left side of Pollux. So mostly open clusters, not a lot of nebulosity, and very dim galaxies. So of the two nebula that we can actually reasonably that are reasonably accessible to us, at least photographically, one is IC 443. This is the Jellyfish Nebula, not to be confused with IC 434, which is closer by. It's actually another alternative designation for the background nebula of the Horsehead. So I getting these two confused by swapping over the last two digits can lead to semantics. But this is 443. And it is a supernova remnant. The star itself is currently thought to have died around 30 to 35,000 years ago. And we haven't narrowed down what the exact classification of supernova it might have been. Current evidence is suggesting it was a type 2 supernova. And as we saw in the previous slide, it is located near the star Propus, which marks the foot of Castor in the overall constellation asterism. The nebula itself was first photographically identified independently by astronomers Max Wolf and Edward Barnard, and the two were somewhat of rivals to each other. Although I'm not sure how you can consider independent discovery of it with a 2-year separation. So I'm not sure how that one worked out between them. The remnant itself is of interest to the astronomy community because it is actually interacting with a nearby molecular cloud. So there's a lot of interest in studying how the physics of this solar material blends with other star-forming nebula to participate in the process of nucleosynthesis, whereby the supernova remnants provide heavier materials for later star formation, which is in part how we are believed to be able to exist with heavier elements such as iron. The nebula itself is about 45 arc minutes in size and is modestly relatively close as far as some nebula goes, or roughly located at 5,200 light years away. However, being a nebula and a supernova, it is somewhat dim. It is clocking in at 12th magnitude overall in terms of total brightness. So don't expect to be able to see this in visual equipment. As a visual observer, it is definitely a photographic object. So illustrating here, this is an image I took of it last winter, excuse me. We can see here up the top, the bright star here is the star Propus with the jellyfish dead center and a little bit of the extended molecular cloud over here off to the lower right. This was done in a 4-inch refractor, so this is about a 2.5 degree field of view by about 1.5 degree field of view. Again, just pointing out where it is over here. So located very much close to the foot of of Castor here. The other nebula is SH2-274, otherwise known as the Medusa Nebula. It is the only other reasonably bright nebula that we can see with modest equipment in the constellation. It itself is a planetary nebula. It's roughly 10 arc minutes in diameter. And depending on which source you want to listen to, it has an overall cumulative brightness of 16th magnitude. So it is a very faint planetary nebula. You would potentially be able to see parts of it because it's of its small and compact nature, but you would probably need upwards of a 10-inch scope in order to pull it out, especially if you're looking on a very slow scope like, say, a Cassegrain. This object is about 1,500 light years distance, and it was discovered relatively recently by George Abel. He was filling out one of his mini catalogs. It was discovered by him in 1955. And it is located near the boundary line of Gemini and Canis Major. I'll show a picture of its location here, star chart location of it here in a second. So this is just a rough rendering of the image of not of the image of the planetary nebula. So it doesn't really look like a planetary nebula, but it is very small overall. We have basically only half of the shell left from our perspective. So this was done in an 8-inch Schmidt Cassegrain to give you an idea of the field size here, which is about this whole field is I think about the size of the quarter moon. So way up.
We lost you again.
Can you guys hear me?
Yes.
Okay, so I'm just gonna swap mics. If you can hear, while I get my headset reconnected, just to finish this up. As we see down here in the lower left, you can see the object here close to the boundaries.
You guys able to hear me now?
Yes.
Okay. Replace my headset here once I switch over. So this uh, finishing up here with the last object we'll talk about, and then we'll move on to Stephen's presentation, is the Open Cluster Messier 35. This is about 3,000 light years away. It's one of the brighter open clusters that we can see at magnitude 5.3, but it roughly has a combined area of about 28 arc minutes. So technically naked eye visible if you know where to look, but definitely one probably better off with at least binoculars just because of its small size overall, especially with its low concentration. It's not potentially visible like you would say with the double cluster. This open cluster was first discovered in 1735 by Philippe Chassot, working, out of the Paris observatories, and eventually passing off this designation over to Charles Messier for his "here's things that aren't comets" list. This is also visually interesting because the open cluster is relatively close to a second, much smaller and more compact open cluster known as NGC 2158. This is a star chart showing the location of the open cluster, so it is relatively close to the Jellyfish Nebula, over off by Propus. You will notice here that there's this other nebula here that's NGC 2175. This is actually within the constellation Orion, so that's why it's not included in this talk. So this is a simulation showing the extended nature of the open cluster. So this is done through simulating what it would look like through an 8-inch Schmidt Cassegrain with a 25 millimeter eyepiece that has a low angular field of view. So you can see that most of the star cluster is available in a very small area. And we have what looks like a globular cluster over off to the right-hand side in this image is actually that second open cluster of NGC 2158. And this is, for those who might be doing photographic targets, this is an image of the overall open cluster. So you see these still have some of that central core density dead center of the frame, and overall the second open cluster up here to the left, not to be confused with a globular cluster. And that's it. Questions, comments on Gemini before I pass this off to Stephen and go find me a different headset that's not cutting off every 5 seconds.
I got one for you. I think the chart of the orbit hierarchy for Castor looks like I think it said like 9 days and 2 days. Am I reading that right? Those pairs orbit each other in a matter of days.
Yes.
Wow. Do we know what the orbits of the three pairs what the period of the orbits of the three pairs are.
I did not see that, and I also was kind of confused why it wasn't included in this diagram, so I didn't
Uh-huh.
include it. But I do not know off the top of my head. Well, you would
Yeah,
probably be able to find that out with similar
yeah,
figures.
just curious. I'm sure it's a very complicated orbit. I wonder if they can even tell what a period would be
Well,
for a six body. uh,
well,
um,
you would measure the orbital period of the A pair and the B pair as those two itself collectively move around the C pair. So, but given
uh,
they have an angular separation of 71 arc seconds, I'm betting it's on the order of thousands of hundreds of years.
okay.
That's a very wide separation compared to, down here, at 3 arc seconds. So, you know, ballpark estimate of, 4 arc seconds is, roughly 20 times that of 71 arc seconds. You're looking at minimum 180 days, maybe, but certainly probably, more, since this doesn't scale linearly. I think it's quadratic, so it's kind of definitely be on the order potentially of years to see a full. Uh,
Cool. Yeah, thanks. That's bizarre.
yeah. And if there's no other questions or comments, Stephen, turn it over to you. Kick off, kick us off with comments while I swap to a different headset.
All right, give me just a second to switch over to the share, and I'm assuming since the green light is on, you can hear me, and I'm just going to put my camera on and see if that'll work. There we go. It's a little washed out, but we'll go with it. Um, I'm going to go ahead and share my screen with this, and then we're going to go over to what should be the Zoom presentation, the PowerPoint. Um, so tonight's general topic is going to be comets. Comets seems like something that is going to be, I'm looking to slideshow from the beginning. Comets would seem like something that is going to be relatively simple, but there's actually all sorts of angles that we could be taking this from. So I kind of had to limit what to talk about. So there are other topics that could be pulled out of comets, like the history of comets in terms of cultures and peoples. These things have been visible as long as there have been human beings, and much longer than that, in fact. So there are many types of lore and mythology surrounding comets. Sometimes the ones we think of are not necessarily the traditional view of them. There's also photographing and diagramming comets, which I didn't really go into either, which is a whole process in itself, probably worthy of its own discussion as well. So this is a very basic sort of intro to comets, meant for, again, we are the beginners group, so, or the general interest group. So this is probably not going to cover everything that goes into comets by any measure, but I did want to kind of just give a brief survey of what comets are and what they're all about. Now, one of the reasons I want to do this now is we just had a couple of bright comets in the sky right now, and one thing I meant to put in this but didn't have time to was a different type of comet, which is, of course, the interstellar comet. And I did not have a lot of time to go into that. That's also an interesting topic in its own right, but I think we're going to skip that for tonight. But it is visible. It's currently in Virgo. And if you want to get up really early, which some of us do, and go out in the cold, it is not a visual object, but with a big telescope, you could probably pick it up. But earlier this year, there were a couple of bright comets, and one of which was Lemon, which we saw from Tampa pretty well, and had some photographs that I think I put in here, maybe not put in here, and then Comet Wise as well. But at any time, you can have 3, 4 comets in the sky that are telescopic. Getting a bright visual one is a little less common. But that's one of the reasons I want to do it now is we just kind of had a rush of comets, and hopefully there'll be some more coming up. They are unpredictable, as we'll talk about, but it's a good time to just go over this. So what is a comet? we all have a basic concept of what a comet is. It's a bright, fuzzy thing with a tail. That doesn't quite capture all the details, but that's sort of what we all think of. The problem is that comets actually share several characteristics with asteroids. And there may be crossovers. For example, it's possible some C-class asteroids are actually depleted comets. Now, whether that is the case has not been confirmed, but it is one thought that that might be, especially the ones that are in the inner solar system, might be comets that have essentially lost all or most of their ices. And some short period comets may eventually become more asteroid-like as they become depleted of their ices and their volatiles. But the key to defining a comet versus an asteroid, at least in terms of identification, is the presence of a coma and a tail. And I'll go into some detail about what a coma and a tail are all about. I think we all know what they look like. At the minimum, you have to have a coma, and if an object produces neither, it's typically classified as an asteroid. And so there are also objects which are at great distances from the sun, Kuiper belt objects, centaurs, things like that, which, if they got closer in, would probably have some sublimation of their ices and produce a coma and a tail. But because they never come that close in, technically they are considered more asteroid-like or classified along those terms than necessarily as comets per se. So parts of a comet, I apologize for the grainy nature of the image, but I will go through these. There is a two-part tail. One part is the plasma tail and then the dust tail. And there is a general wispy hydrogen envelope. But the other two parts that are present are the coma and, of course, the nucleus. And the nucleus is probably the part that you can't see through conventional telescopes, especially when you have a coma already formed in a tail. But it is a critical part of the comet because it is, of course, the source material for everything else. Comet tails are the part that we all think about and we all want to be able to take pretty pictures of and see in the night sky. Comets actually produce two tails. There's the plasma tail, which is charged gas pulled off a comet by the solar wind, and it tends to be relatively straight. And there's the dust tail, which is slightly slower moving stuff that is heavier, larger compared to plasma, that's being erupted off the nucleus and then pushed out into space by the solar wind. And the dust tails curve a little bit more than the plasma tails. They are slightly heavier and the particles are probably not moving quite as fast. Both tails may stretch 10 to hundreds of millions of miles. And the tails always point away from the sun and flow with the solar winds. You might think of these sort of like flags in the wind, except the wind in this case is particles being blown off the sun, and the tail basically is blown by the wind out into space. We, of course, see them from different angles depending on where they are in their orbit versus where we are in their orbit versus where the sun is located. So we can see things from different geometries and the like. Now, some comets do sprout anti-tails. They too are being facing away from the sun and away from the solar wind. It's just that they are at an angle where, from our point of view in the sky, it looks like the anti-tail is pointing in front of the comet. But again, because of the physics, anything coming off of a comet pretty much is going to be blown away from the solar wind in like a windsock. So that's just a general rule, although we sometimes have the illusion that it's not. So comas are dust and gas and plasma being emitted from the nucleus. It forms a very fine, what could be considered atmosphere, exosphere around the nucleus, but it is glowing in part from a little bit of reflected sunlight, but also some of it is ionized, so there is some internal glow. Typically, they're the first part of the comet to form. They will form at distances several AUs out. About 5 AUs is typically when these things start showing the first signs of what they generally just call activity, that they are not just a hard lump in space, that they're emitting gases and dust that gets blown off the surface. It's also true that some comets may only form comas or very weak tails depending on their ice content, their distance from the sun, and the strength of the solar wind at the time. And so what we think of as the head of the comet. And different comas and different tails will have different proportions. So every comet is a little bit unique, which is one of the fun things about them, is that they all there are the sort of very distant cold comets, which only form a little hazy dot. But when they come in close and you get a good view, you can have all sorts of different ratios between the size of the coma and the size of the tail. And then there is the nucleus. This is the solid part of the comet. It's usually not visible once the coma has formed, at least through amateur telescopes. It's one of the reasons we send probes out to comets, is because the best you're going to see of most of these things is a little dot on a survey film or survey picture. And although it is tiny compared to the rest of the comet, it contains almost all the mass. The bright, pretty stuff is very, very tenuous. Most of the mass is contained within the nucleus itself. Now, the nucleus can come in a wide variety of sizes. The smallest are just a couple miles across. And that's more typical. They tend to be fairly small compared to asteroids, but the largest one, I believe it was Hale-Bopp, which they have had some argument over the exact size, but somewhere between 60 and 100 kilometers as a big range would seem to be appropriate for that one. The reason it matters, not just from a scientific standpoint, but of course, every once in a while, it is possible, because these things are coming in on pretty random orbits, for one of these things to hit something. And of course, a big one is going to do a lot more damage than a small one, although any of these things are probably going to leave a mark. So there is interest in how big the nucleuses are. Fortunately, most of them are not 100 miles across or 100 kilometers across, but that does occasionally happen. So here's a picture of some of the nucleuses that we have been able to photograph with probes. This is Hartley 2. And one of the things you'll notice with a lot of these is, not all of them, but some of them, is that they are double objects. They are one single object, but they have lobes. It's interesting. This is also consistent with what was found with the one Kuiper Belt object that has been photographed, which is Arkoth, by New Horizons, of essentially, these are sort of along the lines of a contact binary. These two might have been separate objects that came together and then formed a sort of a dusty bridge between them. You'll see the jets spewing off of the comet there. They're a little bit overexposed. These tend to be very dark objects. They're usually almost coal black. And so in order to get a good picture of the nucleus itself, you need to overexpose the jets, but you get a sense of what that looks like. The ice underneath the surface is sublimating and exploding out into space. And this is a closer view of that one lobe that gives a better view of what the jets are. That one end is about half a mile across. And you can see where the jets are coming out. One of the things that you're seeing is those sparklies. The comet is emitting gas, but it's also emitting little bits of dust and flakes and things. They're sort of like very tiny snowflakes of not necessarily ice, but of finally not very well compacted material that might be organic or silicate in nature. But comets are not just emitting gas, they're emitting little particles that go out too, which then form the dust tail. And so you get a sense of what that would look like. It would probably, what you're looking at, could loosely, in a very wide sense, be considered a little bit of atmosphere, but we're talking about very low density. Probably more exosphere would be a way to describe it. The particles wouldn't really be impact. The atoms wouldn't necessarily be bumping into each other very much. It's just heading out into space. This is Comet Wild. And it again was a little bit further out, a little more depleted when the pictures were taken, so we're not seeing the jet activity. One of the things that's interesting about most of the comets, and I'll go back to Hartley for just a second, is one thing you haven't seen a lot on these comets is deep craters. And that was also true of Arakoth, which was ever so slightly surprising to some of the scientists who were looking at it, is that some of these things coming in from the deep solar system don't quite have the impact history that some of the asteroids do, and certainly some of the moons of the planets do. Why that is open to some debate. One thing is these things are probably being slightly resurfaced by all this surface activity, but when you look at these depressions on Will, they can superficially look like impact craters, but chances are they're areas that got hollowed out as the ice is underneath them sublimed and the very weak gravity pulled material closer to the center. And then other things about the composition of the nucleus is they're a combination of silicates, organics, and ices. They've been described as dirty snowballs. The photographic evidence suggests it's more snowy dirt balls, which is also true of the stuff going on in the outer solar system. Although that it tends to have a little bit more ice for reasons we'll talk about in a second. But it is a combination of things like our Earth rocks, a fair amount of organic material, and then of course what we call ices, things that would only form a solid under very low temperatures and pressures. So, what are some of the organics? The exact maximum complexity is unknown. We don't have really good surface samples. One of the things that there was a probe that went through the coma of a comet called Stardust that did pick up little particles, and it did show some fairly complex organics, but how much that is damaged as it gets blasted off the surface, we don't necessarily know, or by solar radiation. But in M&M, some simple organic materials are there. Organics, of course, are being molecules, including carbon, but usually ones in a chain or in a ring form. Typically, depending on which chemist you talk to, carbon monoxide, carbon dioxide, and methane may or may not be considered organics because they don't form chains as just one carbon. But they are certainly present on comets. But they are considered ices because they, of course, melt and vaporize at very low temperatures. So the ices are the parts that we're going to spend the most time looking at, because they tend to be the stuff that gets vaporized and blown out into space that we see. These are volatiles. They're all compounds that vaporize at very low temperatures and are found as solids only when under very cold, or conversely under very high pressures. Comets do not have very high pressures anywhere. They don't have a lot of gravity, so they can't really squeeze themselves very much. And so anything that's going to be icy there has got to be pretty darn cold. On comets, some of the ices, this isn't exclusive, but it can include carbon dioxide, carbon monoxide, methane already mentioned. Water is an important component, hydroxyls, and various. So that one thing I forgot is a large amount of ammonia. NH4 is very common in comets, but the exact contents vary slightly from comet to comet. And then they may also depend on varying depending on whether the comet has been through the inner solar system or is coming through for the first time. If it's a comet that has been through the solar system several times, or through the inner solar system several times, chances are it's already bled some of those ices out into space, so it may not be quite as pristine as some of the others. Now, just to throw in a side comment that I didn't put in writing, one of the big questions about comet nucleuses is that water the source of the water on Earth? And the general consensus is no. And the reason is that when we have gotten samples of or taken spectra of the water in comets, it tends to be different isotopes of hydrogen and oxygen than we have on the water on Earth. So the thought is that very early in this history of the solar system, a lot of the Earth's original water may have been blasted off by the sun or lost into space, and then it was replenished by some sort of extra planetary source. Comets were originally proposed, they've got also that much water ice, why not can't they be the source? But chances are they're not a great source of the ocean water because of the isotopes in there. So comets probably have had a history of impacting the Earth, but in terms of delivering water, it'd be fairly minimal. But again, for when looking at individual comets, the newer or the less time that the comet has spent in the inner solar system, the fresher the ice and the more of it. Comets are generally thought of as being some of the most pristine objects in the solar system, which means that they are made up of the material that came from all over the solar nebula and collected out in the depths of the outer solar system. They were not heavily processed. Meaning that there's not a lot of heat acting on them, and there wasn't a lot of pressure being acted on them, be it by being inside of a planet. So the material is roughly what we consider pristine. It wasn't changed a lot since the formation of the solar nebula. They're also largely undifferentiated, which means that things that were heavy didn't sink to the middle, things that were light did not sink to the surface. They're pretty much just as they are formed. And older comets, meaning ones that have not spent any time in the outer solar system, or pristine comets, I'm sorry, the other way around, ones that have spent a lot of time in the inner solar system may have lost substantial amounts of material due to previous heating. So there's a couple different types of comets. There's that I'm going to cover. There's now interstellar comets, but they're different. They're a slightly different breed. Might be worth it in a few months to come in and do one specifically on Comet 3 I3 Atlas. But I'm not going to worry about that tonight because that's a good topic for another conversation. But there's the short period comets, which are orbital periods that last a few years to tens of decades. They have orbits that typically, not always, but more often than not, tend to be roughly within the plane of the solar system, which means that they're near the ecliptic a good deal of the time. And they're also designated as P, and they have orbits which have been determined to repeat every few years up to a few decades. Then there's the long period comets, which are orbital periods from hundreds to thousands of years long. Some may never return. Many of them will, but it will take thousands to tens of thousands of years. They have orbits that can traverse any part of the sky, and their orbits tend to be very highly eccentric, meaning that they're very elongated, and then high declination, meaning that they are quite a ways away from the plane of the ecliptic. And the orbital characteristics give us some clues to their origins. So for short period comets, many of them probably come, well, first of all, a general idea of the outer parts of the solar system. So there's two, what is considered well springs of comets, of the nuclei. One is the Kuiper belt and one is the Oort cloud. The Kuiper belt is I think I have something here. So the short period comets are thought to be more likely to come from the Kuiper belt. And the reasons for that are, as I'll talk about, first of all, the Kuiper belt, I think we did a presentation on that at one point, but it's basically the outer belt of comet-like objects and dwarf planets stretching out beyond the orbit of Pluto and Neptune. The belt is mostly in the plane of the solar system. And most of the objects are relatively, meaning like they're not perfectly unperturbed, but there are some which are considered in hot orbits and some in cold orbits, but they're relatively unperturbed from the formation of the solar system, meaning they formed in place, but there wasn't enough mass out there to form a large planet. And it is thought that many, if not most, of short period comets came from somewhere in the Kuiper belt. An alternative, of course, is that they were thrown into their current nice ecliptic-like orbits by interactions with Jupiter, but it could be a combination of both, but chances are most of them are coming from relatively close in. Then there is the origin of the long period comets, which is generally thought to be more often to be from the Oort cloud. Now, the diagram on the right is a little bit confusing. It gives you an idea of what we're talking about with the Oort cloud, but it is a logarithmic scale. In fact, we're talking about much wider distances over on the right side than what the diagram shows. If you look at the one on the left, it gives you an idea. There's the outer solar system, including Pluto, is this tiny little thing, basically at the very center of the Oort cloud. Um, and basically, the Oort cloud is consistent of comet-sized objects loaded at extreme distances from the sun. The Oort cloud objects may reach out to or beyond 1 light year of distance from the sun, and the gravitational effects at this distance are extremely weak. It may take millions of years for one of these objects to get anything like what we would call an orbit. And what we call a cloud is actually statistical. The distances between the comets and the Oort cloud are vast. So it would not look like a cloud from space. So where did the Oort cloud come from? Very briefly, there are a number of theories, but the one that seems to predominate is what's called the Grand Tack hypothesis. There's another name for it, and it's a name after a town in France, but I don't remember which one. Basically, a model, the Nice model, which basically says that early on in the history of the solar system, um, Jupiter and Saturn maybe started out further out, um, and Uranus and Neptune were reversed and much closer in. And then because of the effects of gas and the dissipating solar nebula and the tidal effects of Saturn and Jupiter together, Jupiter and Saturn briefly migrated in, and then Uranus and Neptune, because of those same tidal effects, started getting kicked further and further out to the point where Neptune actually went out beyond Uranus. All of that mixing of planets and particles and little things just kicked all the little stuff way, way out into the solar system. And what happened there was as the planets migrated, especially the outer ones, Neptune and Uranus, they swept up the planetesimals and threw them every which direction. Now, some of them may have ended up in the sun or crashing into the inner planets. It's thought that the Great Heavy Bombardment may have coincided with this. Some were just kicked out of the solar system entirely, and then quite a few of them just ended up in the far reaches of the solar system, where if they remain gravitationally bound, they ended up in the Oort cloud. And in that case, that explains why these comets that are coming from long distances also are coming from random directions, as the Oort cloud forms a nice sphere around the inner solar system. And so those comets can be coming in from above, below, to the side, any direction. So one of the other big mysteries of comets is, why do they come in close? And there is no one single consensus on how this happens. It's actually an area of some debate. Some say that stars passing relatively close to the Oort cloud might explain some of it. Occasional nudges from Neptune might perturb small Kuiper belt objects. It has been proposed that passing spiral density waves, the things that create the spiral arms as they propagate outwards, might have some impact. Remember, we're talking about small objects with very little effective gravity, so just a simple nudge might be over millions of years enough to cause something to come in. In spite of what you may have heard, I think we all probably know this at this point, there's no established periodicity with this. Decades ago, there was this idea of Nemesis, which was a planet or brown dwarf that was hanging out at the very edge of the solar system, different from Planet Nine, but it was one where it was thought that maybe as it got closer in, it caused some of the Oort clouds to be dispersed. That has been proven not to be true. Other than that, it's really anyone's guess how these things get knocked into the inner solar system. Neptune is probably as good an explanation as anything. And then for the when those things that are being thrown further in or interact with Jupiter, they end up on these tight orbits that become the short period comets. So discovery and naming. This is a tricky, and I actually simplified this, even though it's got 12 different points in here. But basically, comets are named after their discoverers. And for centuries, and even into the 1990s, most comets were actually discovered by individuals or small groups working with telescopes that were either taking photographs or just doing it visually. Comet hunting was a very popular high-end amateur activity. So if you've looked at every single possible object out there and taking a picture of every possible object out there. They may be going hunting comets for fun is something to do. It's a very involving process that spends lots of nights without seeing anything, and every once in a while you come across something. After the late 19th century, newly discovered comets were reported at first by telegram to the Minor Planet Center at Harvard, and that which is now run by the International Astronomical, or at least affiliated with the International Astronomical. It's actually run by the Smithsonian Observatory. If the comet was then reported and confirmed, the name went to the first person to report it. If two or more individuals are reported within the same time frame, and I do not know what that time frame is, I would assume within a matter of hours, um, they were both names were given to the comet. And the individuals or team discovered multiple comets, as often happened early on, because you had the comet hunters who got really good at it and were able to discover multiple comets. Then a number was assigned to in the order of the discovery of the comet. And if the comet was then determined to be periodic, meaning that an orbit was determined to come into a view of the Earth and in the inner solar system within a period of a couple to a few hundred years, the letter P was added to the beginning of the name, and then there was a number ahead of it representing the order in which was identified as periodic. So to give some examples, these are famous comets named after individuals. So, of course, the best known is 1P Halley. It was the first comet identified as periodic, and it's known as, or Halley, depending on how you pronounce his name. Halley was the first to identify it as periodic. It had been seen many times before that, but he went back and looked at the records of the comet he actually probably never saw, and realized that there was this comet coming through every 7 decades or so that became visible, was very periodic, and so that was the first to be identified. Hale-Bopp is not periodic, but is a case where two separate people working, I believe, independently found the comet at about the same time. And then there was Shoemaker-Levy 9, which is an example of a team. There's actually two Shoemakers there. That's Eugene and Caroline, and of course David Levy, who we all know. That was their 9th comet discovered together, and so they're number 9 after that. Hyakutake is a comet that I remember very well from when I was in high school. It was the great comet of 1996. There's no 1P. It's not a periodic. It has a very long orbit, and it was not. Hyakutake at that point had not discovered any other comets. As far as I know, he never did again. And there's a series of periodic comets discovered, decades or centuries ago. 19P Borrelli, which we'll talk about. These were all visited by probes. 81P Wild, 9P Temple, and then 67P Shermanov Grasimenko, which we'll talk about a little bit later because it had a special visitor. More recently, comets have been found mostly by sky surveys, many of which were designed specifically to search for comets and asteroids. One of the most prolific is right up on the mountaintop behind me. It's the Catalina Sky Survey. There's also the Pan-STARRS Skywatch, which was one of the early surveys. Atlas, which is a recent survey, been very productive. It was originally meant to be a last chance survey for things that were getting very close to Earth, that were either about to impact or go right past us. NEO-WISE, and we'll go through several of these in a minute, is actually based on the WISE spacecraft. So that was one of the ones that was done actually from space, Linear, and then others. So Catalina Sky Survey, this one is a hometown favorite. Couple different telescopes used consistently. The large one you'll see in the middle of the picture on the right is actually not that large. I believe it's the 24-inch Schmidt up on Mount Bigelow. Also used by that survey is the 60-inch telescope for more narrow field views on Mount Lemmon. Another one that has produced quite a few discoveries is Pan-STARRS. Pan-STARRS was originally conceived of as a cosmological survey, but of course has been very prolific in finding comets and asteroids as well. It is an automated survey, but of course, obviously, there are people who interact with it. But it's been very productive in finding comets and asteroids as well. I couldn't find any good pictures of the Spacewatch telescope that I could confirm are the current scope, but Spacewatch is an older survey that is done off of Kitt Peak, so not quite hometown, but pretty close. It hasn't. It was one of the early surveys. I believe they're still there, but they haven't been as active as Catalina Sky Survey in finding things. Atlas, actually, this is just one telescope of Atlas. There are two in Hawaii, one in South Africa, and I think the third one is somewhere in Europe. But they are looking at most of the sky most of the time for objects that are sort of incoming, meaning they're about to go straight past us very close to Earth or about to actually come in. And they have actually identified one or two objects before they actually entered the atmosphere. Now, of course, when you take all those pictures of little dots moving around, you're going to find some comets. They've been pretty active with recently with finding a lot of comets. NEOWISE was for several years a very productive instrument. It was the requisition WISE survey telescope being used to find objects in the infrared in orbit. Of course, it's not producing anything anymore because they shut down the survey, the telescope, but for a while there it was a very active system. The future, just coming online as we speak, is the Vera Rubin telescope. This is a all-purpose survey. Its primary goal, like Pan-STARRS, is cosmological, but it is going to find, incidentally, tens of thousands to millions of different small solar system objects, including probably a very large number of the comets that will be discovered in the next 10 years. So because it is covering such a wide field of the sky so quickly in such depth, it kind of has an edge, especially in the southern hemisphere, of comet hunting. Also, we have actually humans have sent quite a few probes to comets over the last 30 years. Comet Halley was visited by no less than 6 during the 1986 apparition. And most of those were not very successful. The only one to get a really good picture was Giotto. Our probe was ice. It passed by a very wide distance due to some errors that happened with it. Vega 1 and Vega 2 were Russian, and Susei and Sakakake were Japanese. Suisse were, but only Giotto got in close. 26P Grigshop, I forgot to put which. I believe that was ice as well. They did have a pass to that that comet as well. A little more recently, Deep Space One went by 19P Borrelli. Stardust did a sample return of particles from the tail and coma from Comet 81 Wild. 9P Temple was Deep Impact. And that was of course, the one that had the impactor which crashed into the surface, and then they took pictures. And then 103 Hartley was basically the repurposed deep impact probe under a project called Epoxy. And then, of course, the most thorough investigation of a comet was by that very long named 67C Churyumov Gerasimenko. I'm sure I'm butchering that, which was orbited for several years by Rosetta. And there was the small Philae lander, which did touch down, but sort of tipped over and bounced all over the place. And so they didn't get very good or long data from that. But they did get very, very good data from Rosetta. And they did a very thorough job. It was a European probe of examining the nucleus. And my last thing in here is the future, comet mining. If we were to ever do this, it would almost certainly only be the short period comets, because long period comets are too unpredictable. and their orbits are too eccentric and inclined to be able to reach very easily or get anything back. So we're really talking about something that is already in the ecliptic. We already know where it is and is in a relatively nearby orbit where we can bring things back. Certainly the volatiles like water, carbon dioxide, methane, and ammonia would be very valuable on volatile star worlds like the moon or some asteroids. And certainly the organics might be valuable too. But there are only so many periodic comets. There are new ones being discovered, but chances are not going to be really great ones for that. It's technically challenging, and it might be just a little bit dangerous to change the course of a comet to bring it closer to Earth, and complicated to remove the volatiles on the comet and then pass them back to wherever we want to send them. So that very quickly is the introductory lesson for comets. Any questions, comments, thoughts? All right. Okay.
Thanks, Stephen.
Very good.
Cool. Thank you.
Mm-hmm.
And with that, I think we'll see everybody again in the new year. Or
Thank you.
in case of some of you, see you on the temple tomorrow night. Have a good one.